thanks to the organizers for the opportunity to be here. So today I'm going to talk about critical aging and relaxation dynamics in long-range systems. So let me just go to long-range systems. You're probably aware, but basically we have systems where the interactions, like consider an aging model, for example. So we have a spin one that connects to everybody else on the lattice, and the interaction goes like I minus j, the distances between two spins, with the dimensional space, and then sigma is a parameter. So this parameter governs the power of the interaction, and there are, in equilibrium, the critical behavior is characterized by a mean field behavior when sigma is particularly small. Then there is a regime where we have critical exponents which depend on sigma, and then if sigma is too large, we reduce basically to the standard short-range behavior, the one that you all know. What we want to study here is the dynamics triggered by a sudden quench. So basically we prepare our model at a high temperature, and then we change the temperature to the critical one. And we have two regimes in our dynamics. At short times we have this so-called aging regime, so we observe some scaling which is non-standard. And then we have a long-time relaxation, and we want basically to characterize, to obtain these exponents theta and exponent z, which is a bit more common. Probably you all know about z, but not about theta. We use a model A dynamics, so a non-conserved order parameter, and we have to impose some special initial conditions for this kind of thing. From the technical point of view, we map this to a field theory using the MSR procedure, and then we use a functional renormalization group, which is some non-perturbative technique. What is known so far is the following. So we have the exponent z and the exponent theta as a function of this parameter, the long-range parameter. There are some Monte Carlo studies. And then there are also the perturbative expansions. And what we have obtained is these points here. So we see that we reproduce basically for small values of sigma, so close to the mean field regime, we obtain something very similar. And then we go away from the perturbative results, and we approach a bit more closely the Monte Carlo results. And this is even more apparent for this non-equilibrium exponent, the aging exponents, that we reproduce quite well if the Monte Carlo data are to be trusted. So this a possible application is to use these systems inside the critical heat engines that I found out quite recently. There is a paper of Campisi and Fazio. But this I will discuss. I mean, if you're interested, you can ask me at my poster. And in general, what I want to stress is that this is a generic non-perturbative tool to explore critical dynamics. So what I was really interested in here is critical dynamics. Possible future applications, maybe not so interesting for this community, is quantum. So update this phenomenology to quantum systems, but there is also a possibility to introduce disorder to see if this phenomenology is robust under disorder. And maybe more interesting for this community is memory effects or even active field theories, because so far this was out of equilibrium, but maybe not out of equilibrium enough for you. So we could try to study active field theories. There is actually recent work that uses a similar methodology of a functional renormalization group, and we could try to actually give some estimates of the critical exponents at these fixed points. Thank you.